everyone. Thanks for joining this session. If you attend this talk, please let me know in the chat or in our Slack channel, so I know you are here and everything is all right. I'm gonna share my screen now so we can start the talk. Okay, I'm sharing my screen. Hopefully you can see the slides. And yeah, let's start the talk. So I'm going to talk here a little bit about encryption on embedded Linux. My idea is to try to demystify this talk for embedded developers. So we're going to cover concepts and a little bit of practice. So I have here planned a few hands-on my terminal on encryption using symmetric and asymmetric keys. So I think we're gonna have fun doing this presentation. Let's see how it goes. Before I start the talk, a little bit about myself. So my name is Sergio Prado. I've been working with embedded for 25 plus years. I am located in São Paulo, Brazil. Here I have a company called Embed Labs, where I do a lot of training and consulting for 10 plus years. For the last year or so, I joined Toradex. I'm a team lead there, and I am helping them to lead a team that is developing an embedded Linux distribution called TorizonCore for Toradex modules. Also an open source contributor, so I contribute to a few projects like Buildhood, Yocto, and the Linux kernel. I have also a blog, embeddedlinux.org, where I write some technical stuff there. And yeah, that's basically about myself. This talk is, the agenda for this talk, we have 3 topics. We're gonna start with some introduction on security and encryption. Then we're gonna have basically 2 big topics on encryption. One focused on data at rest. That means encrypting data stored on devices like NAND flash, eMMC, hard disk. And the other topic, data in transit. So encryption on communication channels. So that's going to be our focus here. And as I already mentioned, my plan is to do a little bit of hands-on after each one of those topics. Feel free to write any questions in the chat or in the Slack channel. I will try to monitor from time to time and answer your questions during the presentation. Before we start, it's important to say that I'm not an expert in cryptography. Far from that. I am an embedded software developer. Been working with embedded Linux for almost 15 years. And I have done several a lot of work on the security side of things. So secure boot encryption. So I know a little bit about this topic. And my idea here is to demystify, as I already mentioned, what is really encryption, how does it work, what are the tips and tricks to work with encryption. It's important to know a little bit about the concepts, but also know how to apply those concepts. So I'm gonna try to cover both here. Although this topic is not, it's focused on embedded Linux, I think the concepts can be applied on any kind of embedded development using Linux or bare metal software. And hopefully we will have some fun with hands-on here. Some people say that we have those 3 words, Confidentiality, integrity, and availability are the three main principles of security. And when we talk about encryption, we are really talking about confidentiality, right? If we go to the Wikipedia page, what they say about confidentiality is the property that information is not made available or disclosed to unauthorized individuals, entities, process systems. That's the concept of confidentiality. You want to hide something from someone, right? Why should we care about confidentiality on embedded? I can see a few reasons for that. First, you may want to protect your IP, your intellectual property. You may have sensitive information in the device. You may want to prevent threat actors. I really don't like to say hacker because I think hacker is a term that is misused. So threat actors, so everyone that it is a threat to your system, may want to extract the code to reverse engineering, maybe to find vulnerabilities, or maybe to create a copy of it. You may have threat actors trying to extract data, and you want to protect it for privacy reasons. And sometimes you even need to do that, right? Depending on the product that you're developing, let's say a medical product, you will need to comply to some regulations, and then you will really need to care about like privacy, data privacy from the users, for example. Then encryption may be one of the solutions. And when we talk about confidentiality on an embedded device, we may care about data confidentiality and code confidentiality. Now, data confidentiality, we usually separate it in three different aspects. We have data at rest, that's data that's stored in your device somehow, flash memory, eMMC, hard disk, or somewhere else. We may have data in transit, that's data that you are sending, like it's you are using a network connection, could be an Ethernet, Wi-Fi, Bluetooth, any connection, and you are sending data to someone and you want to hide this data, you're going to have to protect it. The third type of data is data in use. That's the data you are currently using, right? Like data in RAM memory, data in the CPU, cache lines, for example, registries. So you may want to protect also that. In this specific case, you probably need some kind of hardware support, right, to protect data in RAM. Let's say you want like online protection. If someone is able to exploit a vulnerability and access your system while it is running, it may like the threat actor may be able to see what you're running, dump the RAM memory, and then if you have secrets there, you may have problems. In this specific case, you may want to hide. That's not really usual because usually I say when we talk about security, we are talking about risk management. And in the risk management field, you always have to think about what are the risks and what are the costs to mitigate this risk. And when we think about data in use, the cost to mitigate this specific risk is really high. So you have to think about twice if you want to really protect this kind of information. So it's always a risk management thing, security. In the presentation, we're going to focus on data at rest and data in transit. But I can also mention that code confidentiality may be another issue. This is also not common, especially on embedded Linux designs, because when we are designing an embedded Linux system, we are basically building on top of several open source projects, so there is nothing to be hidden there. But let's say you want to hide your application, right? You don't want your application to be really visible to anyone. Like if someone is able to dump the flash memory of your device and extract the code of your application and disassemble it and recreate it and do reverse engineer on it. Maybe if that's something that you care about, you will probably need to think about encrypting your application. But usually you don't need to encrypt the full operating system, especially if you are using or developing an embedded Linux device where most of the open source of the software is open source. Another problem with encrypting code is the license, because if you are designing with software that's GPL v3, due to trivialization, you may have problems because GPL v3 says that you need to provide some way for the user to update that software in the device. So if you are encrypting a software that's GPL v3, you're going to have to basically provide the keys for the user to encrypt and update the software then. And that may be is not really what you want, right? Because if you are encrypting, you need to really protect the key that you are using to encrypt and not provide this key to everyone to encrypt their own software. And so that can maybe a problem. You can work around this, but usually you really need to design in a way that this will not be a problem for you. How can we solve this confidentiality problem? Encryption is one way. So you encrypt data in a way that's not readable, and that's it. But there are other ways to solve this problem. Another way is authorization. So you want to control who has access to the data, for example. You can implement an authentication mechanism in the device, so only the authorized person can access that data. Tampering is another technique. So you can have you could have a tampering system where if a user, for example, opens the device, then physical protection would trigger an erasing in the flash memory, for example. So you erase everything, so no one will be able to access the data, for example, from your device. And this talk is really about encryption. So what is encryption? Encryption is the process of encoding and decoding information. That's basically it. It has basically three main components. You have a cipher with some kind of secret. The cipher is the algorithm, and usually it is public. You know what the cipher is. The cipher is not really a problem. You really need to care about the secret that you are using as input to the cipher. This plain text is the input, and the cipher text is the output for an encryption process. For decryption is the inverse. So that's the main idea, right? That's represented in this diagram. We have the encryption on the left and the decryption on the right, and some kind of secret to do the encryption and the decryption. This is a very simple example. It's a very known cipher called Caesar cipher, used hundreds and hundreds of years ago. You basically shift characters. So here we have the plain text in the bottom, and here we have the cipher text, right? Here I'm doing decryption, actually, right? So I would take the cipher text, my cipher, that's a shift. We can say that -3 is the key to my cipher, is the input to my cipher, because I'm shifting -3 characters to decrypt the message, and here is the decrypted message. So that's basically the concept of encryption and decryption. There are two main types of encryption keys or encryption algorithms. We have symmetric keys or symmetric algorithms, and we have asymmetric keys or asymmetric algorithms that we also call it public keys or public-private keys or key pairs. The main difference between those two is with symmetric encryption, the same key is used for encryption and decryption. And with the asymmetric scheme, you have basically a pair of keys, a public and a private key. You can encrypt with one key, and you will decrypt. You need to decrypt with the other key. So they they are used exchangeably. So you can decrypt with one and then encrypt with the other one, and vice versa. There are some mathematical properties in the algorithms that make that happen. So this is a diagram representing the encryption process. The same key is used for encryption and decryption. And this is really the weakness of symmetric encryption. How can we share this key? This is really the big problem. How can we share this key in a way that you can encrypt and decrypt the message? And when you talk about an embedded device, the problem is how can we safely store this key in the device? We're going to discuss this. In asymmetric encryption, you have two keys. You have a public key and a private. If you encrypt with a public, you're going to decrypt it with a private. So here, that's nice because everyone can have a pair of public and private key. So let's say I want to send a message to someone, and I want that just this person will be able to see my message. What I can do is take his or her public key, encrypt the message with this public key, and then only this person will be able to decrypt it, because only this person has the private key or the secret key. We're gonna also see that there is no like a best option here. It depends on your use case, right? There are trade-offs between these two algorithms, and I'm trying to represent this in this table. So as you mentioned, symmetric one key, asymmetric two keys, or a key pair. A symmetric algorithm is really lower in terms of complexity, and that means in practice that it will run faster and we will use less resources. If we compare with an asymmetric algorithm, it will be higher in terms of complexity, and that means in practice that it will run slower in your device and will use more resources like CPU, memory. So there are trade-offs here. Usually symmetric algorithms are able to encrypt large chunks of data, and asymmetric only encrypts small chunks of data. In the end, we have a kind of examples of the most common algorithms. So for symmetric key, the most common block cipher. For symmetric key, we can have block ciphers and string ciphers. That's the way the algorithm works. Encrypting by blocks or bit by bit. The most common block cipher is AES, and the most common, I really don't know what is the most common string cipher. I would mention two that I know that is used, RC4 and CHA-20. For asymmetric key, the two most used are RCA and the elliptic curve cryptography ECC. Those are the most common, at least as far as I know. And they really complement each other. Like, if you want to encrypt files, you're gonna probably do symmetric encryption because it's faster and it is able to encrypt large amounts of that data. Now, let's say, for example, you want to sign data. For signing, you're gonna probably use asymmetric key because you're gonna basically, signing data is basically hashing data and encrypting the hashes, the result from the hashing algorithm. And the hash is small, you can sign with an asymmetric key. The other use case for asymmetric key is exchanging private or exchanging symmetric keys. And they are really used in conjunction. For example, we're gonna, in the end of the presentation, talk about TLS. And TLS is basically using both. So you do the encryption with a symmetric key, that's called session key. And the session key is generated at runtime using asymmetric key to exchange this secret. So the asymmetric key encryption is used to exchange a secret that's a session key used for encryption during a TLS session. Now we have our first hands-on. Let's see how it goes. I'm gonna share my terminal right now. Hopefully you all can see. Let me know if you have any problems. We're gonna play with encryption and decryption using both symmetric and asymmetric algorithms. So let's start with symmetric key algorithm. So first, I'm going to generate a key. I'm going to use OpenSSL during the presentation for the hands-on. It's a nice and simple tool to use to learn and work with encryption. So here, what I'm doing is I'm using OpenSSL to derive a key from this passphrase. It will basically generate a key for me. That's one way to do it, because a key just handle data. I could like a cat dev view handle from my machine and generate a key. It's just handle data. More handle the data is, the better the key. That's one of the reasons a handle number generator on a system where security is important is an essential device. So here I'm going to derive the key, and now I have the key, this big block of data. I'm going to store this key in a file. Of course, that's not good because you don't want the key in a file where everyone can see, but this is just for this demonstration. So I have a key in a file. Very nice. Now I will encrypt this file, the manifest.txt file. This is a text file from the Frack magazine. I'm going to encrypt with this key. So this is the command OpenSSL encrypt. I'm using here AES. That's the most common symmetric algorithm. I'm using the ECB mode. I'm going to talk about what is this in a while. This is the input, my file. This is my key, and this is the output. Simple as that. And then now I have my output file. I can see that this is just junk, encrypted data. I cannot see what it is, right? It is encrypted. And for decryption is the opposite. So OpenSSL enc-d for decryption. My algorithm, my input is the encrypted file, my key, same key, and my output will be a file with .dec extension. And that's it. Now I have the decrypted file. It should be the same as the original file. So we have just done encryption use AES here. Of course, if I want someone to decrypt this file, I would need to give him the key, and that's the big problem of symmetric key encryption, how to exchange this key. I have used here a mode called ECB. Let me show you how bad is this mode. It is really not recommended to use ECB in real applications. And I'm explain what that means. So I have here an image from our lovely penguin tux. I'm gonna encrypt this image, but only the data from the image. I'm gonna remove the header from the image. I want to encrypt only the body. So I remove the header. I have here the body.bin, that's the real data from the image. Now I'm gonna encrypt it with AES in ECB mode. Same command, same key, nice. So now I have a body.bin.enc for the encrypted data. I'm gonna add the header back to the image, right? And let's see how this encrypted image would look like right now. Can you all see that we have like leak in the process? We can see there we have a penguin, right? That's because of ECB. Let me show you the Wikipedia page that has some nice diagrams about this. So this is how ECB works. It will take every block from the file that you are encrypting and encrypt it with a key. So if you have several blocks with the same content, it will generate the same ciphertext. So for the same plain text, you have the same ciphertext. And in the end, you have exactly what I show you. So this is very bad, because if you have the same ciphertext, we are leaking information. We are saying that, oh, that means that all of these blocks have the same plain text. So if you're leaking information during the encryption process, that's not good. A better mode for encryption is called CBC. With CBC, we have another source of entropy to the encryption process, and this is called, in this specific case, we call it initialization vector. So we are adding here a new source of entropy. And again, this is just handle data that I added to the process for encryption. And then the first ciphertext will be the initialization vector of the next cipher block, and so on until the end of the file. So in this specific case, I can have the same plain text, but I will generate completely different ciphertexts, because I am using more entropy to the encryption process. Now I can show you how that works again in the terminal. Let me first, let me try to now encrypt the body with CBC. It will fail because we need an initialization vector for that. So this is required. Let's generate this initialization vector. It should be 500, I think, 16 bytes. I have it here. So this is my initialization vector. Now I can use it to encrypt the body using AES-CBC. The only difference is this parameter here, where I'm giving the initialization vector. Now I can encrypt it. Then I can generate the image back again. And then I can see that now I have really handle data in the output. Let's talk about asymmetric key encryption. So let me check here. Let's generate keys first. So I'm going to generate here RSA key, private key, using OpenSSL. My key is in this file, priv.key. This is the size of the key. I'm going to create I'm going to extract the private key, the public key from this private key file. Then I have now both the pair of keys that I need for asymmetric encryption. So I have my public key and the private key. The private is private, you should not give anyone, and the public you can give everyone, no problem with that. Nice. Now let's encrypt this small file. So I have here a small file, secret of life, small file. 42 is the answer for that. We're going to encrypt it with AES. So this is the command, OpenSSL. I'm going to use AES to encrypt. The key is this public key. This is the input file, and the output file is the file with .enc. Encrypted. Very nice. I can try to see the content. Of course, it's going to be garbage. Let's try to decrypt it. It fails. Why it fails? Because I tried to decrypt it with my public key. If I encrypt it with a public key, I can only decrypt it with a private key. So that's why it fails. I need to run the command with my private key, and then I can decrypt it and see the decrypted file there with the same content. So you use one key for encryption and the other key for decryption. Now, what if I want to encrypt a big file? I cannot, because how the RSA works is that you can only encrypt files or data with the same size of your key. So I cannot encrypt this file that is big. My key is 4096. So I need now to combine both symmetric and asymmetric encryption. Let me show you how it works. So first, let me create a key. I want a private key for symmetric encryption. I'm creating this key right now. And I'm also going to CBC, so I will need the initialization vector. I'm gonna save both in a file. So let me save here the key in the file, and also the initialization vector in the file. Great. So I have a key. Let's say this is our session key. So in this specific case, the idea is that I will receive a file from someone. So someone will create a session key, that's this key, will encrypt it with my public key, and send to me the file encrypted with this key, and the session key encrypted, so I can decrypt the key, and after that decrypt the file. That's the main objective here. I'm combining symmetric with asymmetric encryption. So I have the key. Let's now encrypt the file with this key. So the same command, I'm running AES CBC to encrypt the manifest file with my key and this initialization vector, and I'm going to generate this encrypted file with the session key that I just created. Now I need to encrypt the session key. So OpenSSL, I'm using RSA. I will use my public key. This is the key, and this is the output. So I'm encrypting the key, and we'll generate an encrypted key. Very nice. What I have now, I have these three files. I have the encrypted key, the session key encrypted with my public key. I have the file encrypted with the session key. And how now I can decrypt the file. Now let's say someone sent me this information. Now I need to decrypt it. The first thing I need is the session key. So I need to decrypt the session key with my private key. So decrypted the key. Now I have the key, right? And with the key, I can decrypt the file. And now I have the file decrypted. So see here that we combined, right, both symmetric encryption to create a session key and encrypt the file, and asymmetric encryption to encrypt the key, the session key, so we can transfer it to someone else. So we are solving that problem with symmetric encryption, is that how can we exchange keys during encryption? What we have done here in the command line is basically how TLS works. Of course, there are more in the TLS protocol, but that's basically how it works. We exchange keys, session keys using asymmetric encryption, and use symmetric encryption for the encryption itself. Very nice. Hopefully this was useful in terms of understanding the concepts, right, of encryption and decryption using symmetric and asymmetric keys. Now let's talk about how can we apply this on embedded Linux. First, data at rest encryption. Data at rest, data stored in the device. We have basically two approaches for that. We can do full disk encryption or file-based encryption. I really prefer full disk encryption. It's more secure than file-based encryption. But you can decide on both. Again, it really depends on what are your security needs, right? For full disk encryption, that is basically one solution, that is DMCrypt. It's a device mapper implementation, Linux kernel. So it sits on top of your block device, between your block device and the file system. So you can use on any file system. And it will basically encrypt at the block level. That's basically the idea. Now, if you want to work with encryption at the file system level, then you have a few options. Two of them are FSCrypt. FSCrypt is a kind of API for a few file systems like SU4 and UFS. And encryptFS, that's basically a layer that works on top of any file system. Here at the presentation, we're going to discuss a little bit about FSCrypt. But before that, DMCrypt. DMCrypt is a device mapper from the Linux kernel. So, as I mentioned, it works on top of the block device and down the file system layer. So every access to a block device will go through DMCrypt that will do encryption and decryption at runtime. That's basically the idea. It will use the kernel cryptos API, and there are a few user space tools that you can use to configure. We're going to see how this works in the next hands-on. This is basically DMCrypt here, as you can see, right? Between the block device and the file system. Really, with 4 lines, you can do encryption at the block level on Linux. That's what we have here. You need to enable DMCrypt in the kernel. We need to decide how we're going to format the disk. The most common format for this is LUKS. LUKS is a kind of platform-independent standard to format disks for encryption. We'll create basically a header in the partition or in the full disk, so you can store metadata about the encryption there. And I'm going to explain about these commands in the next hands-on. FSCrypt, it's basically another way to do encryption at the file system level. So you can basically create a directory, and then you can, when you create a directory, you can encrypt that directory. That's basically it. With 3 commands, you can enable FSCrypt in your device. I would like to go now to the next hands-on and show how this works. So let me switch again to the terminal. Hopefully you can see my terminal again. I am here on a console of a device. I'm running a very small system that I built with Buildroot. I'm booting over the network. So I have my full file system in my development machine, kernel, device tree, everything in the network in my device. But that's not really matter. The idea here is try to understand how can we do encryption on disks on Linux. So the first hands-on, I'm going to do encryption on, I have here a pen drive connected. Oh, I don't have here, okay. I have here a pen drive connected to my device. This pen drive has 2 partitions. So we're gonna now configure this partition SDA1 to be encrypted. We are gonna use DMCrypt for that. So let's do that now. Hopefully it will work. The first thing you need is a key. So that's one, and again, it's one of the problems doing encryption on Linux is the key. Right now, we don't care about this. I'm going to discuss about this after this hands-on. What we can do, how can we store, securely store the keys. But right now, I'm not care about this. So I'm running the same as OpenSSL command again to generate a key, right? I'm going to copy this key to a file. Again, this is very insecure. Don't do that on the device. This is just for demonstration purposes. In theory, you should get this key from some secure place. I'm going to discuss about this later. Right, first thing I need to do, format the partition. I'm going to use LUKS here. So I'm going to use this tool, CryptoSetup, to format the partition with LUKS using this key. This is my key, right? So let's do this. It should take a few seconds, hopefully. So we don't need to wait much time. Good, since it worked, now we can open and create a device mapper for this partition. So crypt setup open, this is my key. Now what I'm really doing here is open the access to this partition because I need a key for that, and I'm using the key to open the access to this partition. I'm calling this the data dir. So it's going to be a device mapper called data dir. And of course, I will need to run this command every time I boot the system. So if I reboot it, I will need to run again to have this device accessible again. Now I have the data dir here, a device mapper. Now I can format. Let's format with ext4. It was very fast because the partition is very small. It's a few megabytes. And now I can just mount it. Let's mount it on /data. Mount it. Now, everything that I store here at /data is going to be encrypted. Let's do this. So let's write something there. So we have data file called secret with content 42. Let's reboot the device and see how it works. It's going to boot over network. Hopefully my network is fine. Booting the kernel, device stream, now booting the, now you mount the root file system via network. Okay, now if I try to mount this partition, I will not be able to do it because it is encrypted, right? We don't really have like an ext for that. It is encrypted. All of the data and metadata from the partition are encrypted. Everything is encrypted. So if I want to access again this device, I need to open again with crypto setup. And of course, recovering my key from somewhere safe. Then after that, I can mount again. And then after that, I can have access to the content of this partition again. So as you can see, it's not that hard, right, to configure an encrypted partition. Of course, if you're designing an embedded Linux device, we're going to think about how are you first create an image with an encrypted partition. So we're going to need some magic at build time for that. And also at boot time, we're going to think about how to store and recover the secret that's our key. That's another issue. Let's now see how encrypting our directory would work. So I have here another partition, the SDA2. The first thing, so now it's basically the only requirement is formatting the partition with this flag encrypt. So here I'm enabling the fscript API for this partition. Let's do this. So take a few seconds. This partition, I think, is 32 megabytes. Great. Now I can mount it somewhere. So far, nothing is encrypted, okay? So we have the partition there, mounted at -data, but nothing is encrypted. I'm going to create a directory there. I'm calling this directory secrets. And then I will create another key here, just as an example, okay? So we can add this key to the system. So I can create another key. I could use the key that I used in the other example, but just to show that key is really just handle data. So I use it dev/dev/handle to generate a key. We can see the content of this key, right? But it's binary data. And now the first thing I need to do is add this key to the kernel key ring with the fscript control tool. This is, I think, a tool that Google developed. Very nice tool and simple. They are targeting like embedded devices because the usual fscript tool, it's big for an embedded device. So I'm using the fscript control. And now I have the what they call the key descriptor. Then I basically enable this key for a specific directory. I'm just enabling here an encryption policy for the data secrets directory using this key. It selected the default algorithm. Now we can see like what are the decisions for this encryption. So we can see here the key decided to use AES for the contents. It decided to use this algorithm, and for the file names, this algorithm. We could decide also the algorithms, but I left it with the defaults. So right now, everything that I write here will be encrypted. Let's do a test here. So I'm gonna again create a secret file here. Nice. And I'm gonna cat the content of this file. We can see that we can read, of course. We added the key to the key ring and enable it. Let's now reboot the device so we can see that it is really encrypted. Again, it will take a few seconds to boot from the network. For those that are asking for the materials, yeah, I'm gonna share everything. I'm gonna share the comments in the Slack channel. I don't think I can do it in the platform. The slides, I think it's already there, but I'm gonna check in the end of the presentation. Okay, I booted. Let's see what we have there. So let's mount again the partition, and we can do this because the partition is not encrypted, so we can mount it, and we can list the partition. So what we have in /data, we have the secrets directory. What is encrypted is the content of this directory and everything inside of it. So if we list this, we're gonna see garbage, right? As you can see here. So the file name is encrypted and the content of the file is encrypted. If I want to access this, I have to run again insert the key to the key ring, and again, this key should come from somewhere safe, right? And then I should have this on the enable it, this policy, and then now I should be able to list the content, and then I can access the files there, right? There are a few downsides that I know on this on FS script. For example, extended attributes are not encrypted. As far as I know, they are not encrypted. So not everything is encrypted using FS script. That's what I mentioned. That's if you want to encrypt really everything from the file system, data and metadata, everything, you're gonna probably have to go with a full disk encryption for that. Very nice. I hope it was also a useful demonstration on how that works. And again, I'm really trying to demystify. It's not that hard, it's not that easy. With a few commands, you can do encryption at the file system level, at the block level on Linux. And yeah, the big problem that we have with encryption is the key, right? Because as I mentioned earlier, could we use like asymmetric encryption, asymmetric algorithm for encryption? Yes, but it will be very slow and problematic. That's why you use symmetric encryption. But the key is the problem. That's our secret that we need to safely store. And how can we solve this problem? If we are working with like a desktop system, we can solve this with a password. So we can kind of use key derivation algorithms, like an algorithm that will take up a string and derive to a password. That's, for example, how Android works, right? When you boot Android that has encrypted partitions, it will ask for a secret that could be a password, that could be some kind of places that you touch in the display, right? the symbols that you write there. I mean, any secret. With this secret, it will use an algorithm to derive the key. That's one possibility. But on embedded, we don't have this option, right? Usually, we don't have we don't interact with an embedded device, right? Usually, don't even have the way to do that, like a display. So we need to work with other solutions. Basically, we need to find a way to store this key securely in the device. And for that, we're going to need hardware support. You may be using some kind of processor with this support. For example, NXP IMX processors. They have this cryptographic module that you can use for that. So every IMX processor that has the CAN module has a kind of master key inside of it that's unique per device. And you can use this master key to encrypt and decrypt your private key. So at manufacturing, you would like boot the device, generate the key, and use the master key from the CAN module to encrypt it. And that's it. So, and every time you boot, you will be able to decrypt this key in RAM and then use it to decrypt a partition. That could be one solution. If you don't have the support in the processor, the SoC, then you probably need an external hardware, for example, a TPM or a secure element for that. Both are basically secure computing systems. A secure element is a more generic secure computing system. So it does secure computation and also secure storage. Two common examples, the SIM card that we have in the smartphones and the smart cards. They are both secure elements. The other option, that at least from my previous experience is more common on embedded devices, is a TPM. A TPM actually is not a device. A TPM is a standard, is a ISO standard that defines functions, cryptographic functions, and secure storage for an embedded device. So, and of course, we have TPM devices that usually provide an interface via I2C or SPI. So you can communicate with these devices, and these devices will do for you those cryptographic operations like hashing, generating certificates, keys, signing, encrypting, all of this. And it provides secure storage, so you can store a secret there, and it will not get out of there. Of course, it will be very difficult for you to get the secret from the TPM device. So you could use your TPM device, for example, to encrypt the key that you use to encrypt the partition. That's another solution. A final solution would be use a trusted execution environment. I would not spend much time on this, especially because we are almost out of time during this presentation. I have two nice posts on my blog about this if you want to check out, embeddedbits.org, where I go over the details of trusted execution environment implementation. I have also a few talks on my YouTube channel about this if you want to check out. But with TE, we can add basically another layer of protection, providing security also at runtime, not only like offline security, but also online security, because you can have a secure road version of your system isolated from the main operating system, where you can run secure functions and use secure hardware to store secrets. Very nice. We have a few minutes to the end of the session, and the last session is kind of quick. I think I will not be able to go over the last hands-on, but I will mention a little bit, and hopefully almost everything we already covered during the presentation. So data in transit is data that you transmit right to some external device or machine or network. So everything that's going out of your device every data that's going out of the device that you want to protect, we're going to think about how can you protect that. Here I would say we have basically two options, depending on the use case. You may want to encrypt the full communication channel. So let's say we have a network interface, and you want to, you really want to create a tunnel of communication with some servers, and everything that goes there is going to be encrypted. Then you're going to probably need a VPN for that, or some kind of VPN setup. Now, if you want to encrypt at the application level, let's say you have an application running that will communicate with a server, and then you want to encrypt the communication, then you're going to probably need to leverage TLS. So for VPN, we have a few options. We can use the IPsec, or we can use OpenVPN that will abstract a little bit the configuration. The third option is WireGuard. And I'm really enjoying WireGuard. I've been working with WireGuard for a little bit now. It's a kind of new protocol. Very simple. It's really designed to be used on embedded use cases. And very simple to configure compared to other approaches. And really, really fast. It's a kernel-based implementation. So that's another option. A very nice option to have VPN support in your embedded device. Now, if you want to encrypt data that an application is sending, you're going to probably need TLS. That usually we use SSL, right? But SSL is kind of the old name of the protocol, and TLS is the new version. Basically, TLS will use both a scheme of a symmetric encryption for the encryption itself and asymmetric encryption to change secrets before doing the encryption. There is a variant of the TLS that's called MTLS or mutual TLS that is used when you want to authenticate both the client and the server. Because we know TLS is used on like communication with a web browser, right? With a web server. So you open the web browser and you go there and type google.com, and then you're going to communicate with Google servers, and you're going to connect using TLS if the server provides a TLS connection. What happens during this process is that the client, your browser, will check the authenticity of the server to make sure that you are really connected to Google, not to some fake server. That's important. But Google don't care about you. So Google will not check that you are you, right? So you don't need a certificate. So Google can check if you are you. That doesn't happen in this communication. Now, with an embedded device, this may be important, right? You have an application that will communicate to your server. You need to make sure that your server is talking to your application. So the server will check the authenticity of the device, and also the other way around. The device will check the authenticity of the server. So both the client and the server will check the authenticity of each other to make sure that they know to whom they are talking to. And to finish the presentation, we are kind of out of time here. This is basically how TLS works. And after our discussion on the algorithms and the protocol, I think now it would be very kind of easy to understand what is happening here. This blue line is represent the TCP connection. We can skip that, and the green ones are the TLS connection. And during TLS, the first thing that happens is that the client will send information about what the client supports to the server. Like, I support these protocols, these ciphers. The server will receive this and take a decision. Okay, so let's use this protocol version with these ciphers. And in an MTLS connection, the server will also request the client for the certificate. And then after that, both the client and the server will check the certificates. And we're not going over how this works, how PKI works and all of this public key infrastructure works. But there is a mechanism where both will trust on each other using a kind of certificate authority. What's important to know here is that one is checking the authenticity of the other to make sure they are really talking with each other. And then after that, the client will generate a pre-master key that's a symmetric key. And this key will be encrypted with the public key of the server, and then the client will send this to the server. Oh, this is my pre-master key, decrypted with your private key, and use it to generate our session key. And then the client and the server will generate a session key with this pre-master key. And then after that, the client will send a finished command. The server will also send a finished command. Both will be encrypted with this key. If they can understand each other, that means they could successfully generate the same session key, and communication starts. So see that again, we are using here an asymmetric encryption with the keys inside the certificates to encrypt the session key and then start the communication in an encrypted way. Very nice. I don't have time, unfortunately, to go over the last hands-on here. I'm gonna publish the comment, everything that I have done here in the Slack channel, and I'm also planning to write a blog post, kind of write up of this talk in my blog in a few weeks. Hopefully, it was a nice talk. Hope you enjoyed this talk. We are out of time. I will try to answer the questions offline on Slack or in the chat. Thank you all, everyone, and yeah, until next time. Bye bye.